So let's focus on an elliptical orbit. For an elliptical orbit, then, we can substitute the semilatus rectum by a 1 minus e squared, and then the rest of the equation is over 1 plus e cosine of theta minus omega bar. Now, theta here is the angle that is measured from the reference direction. This angle omega bar, sometimes also called curly pi, is called the longitude of the pericenter. And although this is a constant for the two-body problem, it can vary with time when you have additional perturbations. So it's usually more convenient to refer the angular coordinates to the pericenter itself rather than to this arbitrary reference line. So we can introduce the angle here, f, that we call the true anomaly, which is theta minus omega bar. So the equation of the orbit then becomes a 1 minus e squared, 1 plus e cosine f. Notice that if you use Cartesian coordinates, you'll have here the quantities x and y measured from M1. X is given by r times cosine of f, and y is equal to r times sine of f. We also know from Kepler's third law that the square of the period is equal to 4 pi squared over mu times a cubed. We define it based on the period, a quantity that we're going to call the mean motion, little n, which is 2 pi over the period. This is a definition. And here is called mean motion. Now, because the period is constant for a closed orbit, so the mean motion is also constant. So using this definition on Kepler's third law, then you can write mu in terms of the semi-major axis and the mean motion. And if you have that the angular momentum square is the semilatus rectum times mu, which is equal to a 1 minus e squared mu, you substitute the definition of mu given by the mean motion and the semi-major axis, as given here, then this becomes n squared a to the 4th power times 1 minus eccentricity squared. Take the square root of that, and you find a simpler expression for the angular momentum. Another constant of motion of the two-body problem is the energy. You can find it by taking the equation of motion again, and then take the scalar product of this with the velocity. So the equation we have is r dot dotted with r dot dot, then plus mu over r cubed times r dot dot with the radius vector. Now, if we use the expressions in polar coordinates for the radius and for the velocity, and substituting them here, we have that r dot dotted with the radius vector is equal to simply r dot and r. So this equation here becomes r dot dotted with r dot dot plus mu r squared r dot is equal to 0. Now this can be integrated and find half of r dot dotted with r dot minus mu over r, then is equal to a constant of integration. Now, r dot dotted with r dot is, of course, v squared, where v is the velocity. So what we find then is the energy equation, also called the vis viva integral. The kinetic energy per unit mass plus the potential energy per unit mass is equal to this constant. So this constant is obviously the energy per mass, and it's a constant of motion. So the two-body problem has 4 constants of motion: the energy integral, c, and the 3 components of the angular momentum integral, h. These are 4 constants of motion of the two-body problem.